Hey everybody. So this is going to be something a little bit different. I also have Tall Cat here, which will be a voice in my ear. So if you have questions during this presentation, Tall Cat will be reading the chat and passing that along, as well as potentially contributing his own questions and comments. But this is a presentation I've prepared. I'm calling it The Anatomy of a Sudoku Variant Solver. What makes a solver correct and fast? So I've actually written several different Sudoku solvers as well as other kinds of puzzle solvers. And I've learned a whole lot over the past at least 4 or 5 years of working on that. And my solver, my one of my solvers is quite popular among Sudoku setters. So my solver is one of the few variant solvers out there. It's also extremely performant, and it's also designed to be useful for the setting process rather than for someone trying to solve someone else's puzzle. So that's just some context there.
They may
To
have
get
actually
started.
seen it earlier on the stream. It does look like my source is coming up, by the way. So yeah, they probably saw it earlier on the stream when I was using the true candidates in the speed solve. So
Great. So if you were watching the stream earlier, you saw it in action. I won't actually be showing it in action because I don't want to kind of mess with sources, to be honest. And this presentation will be long enough as it is. But hopefully, either you have context or I'll be able to give enough context. So let's start with this. Who am I? Well, I go by Rangsk online. These are my various handles. So on GitHub, that's where you can find all of my various open source projects, many of which are Sudoku solvers. There's one in C Sharp, which is my most popular one. I also have a partially implemented Rust port of that solver, which also can compile to WASM. And then I have a TypeScript solver, which has been contributed to by others as well, especially GraceFu. I am a programmer by trade. I've been programming professionally for, I think I counted it as 19 years, but it's 30 plus years if you count unprofessional programming work. Um, we also I am a setter myself of variant Sudoku. I'm not exactly prolific, but the ones I make people seem to like. And also, I am a content creator. So as you can see, I'm on YouTube, TikTok, Facebook, Instagram, and I do word games and puzzles. I do the New York Times Hard Sudoku every day. I also curate and present the Sudoku Adventure series, which are 6x6 variants. So if this makes you at all interested in variant Sudoku for some reason, I don't know why this particular presentation would, but it is a great introduction to that because they're much smaller bite-sized puzzles, and we can just boil down to the most important logic of variants you might encounter. um, Gives a lot of
I,
variety. It's a daily series, and we're actually about to hit number 1,000, so we're going to do something special for that.
I want to
Did you
say,
have something, Talcott?
Lance, yeah, I was going to say, it's in my memory that you actually were relatively key in sort of repopularizing region sum lines, because I seem to recall you setting a couple that were featured on CTC and then they suddenly took off again. Am I right in that?
That's about right. So I actually coined region sum lines. I did not invent the variant. There was actually one or two puzzles that CTC featured, and it was called equal sum lines at the time. And I saw that and I was like, "Oh, this is really interesting." So I actually implemented it in my solver. And when I talked with people in the community, they said there's already a constraint called equal sum lines, which are all the lines in the grid have the same sum as each other, which is very different than region sum. So I came up with the term region sum. I didn't want to call them box sum lines because you might want to do it with irregular. But so I coined region sum lines because I had to call it something when I added it to my solver and to the fpuzzles integration. And
Right.
then I also set a pretty seminal puzzle um, that was featured on CTC, and then from there it just took off. Half because of the popularity of that puzzle, and half because I added it to the solver, so it was another option in the menu that people played
Okay.
with.
Okay.
So
Cool.
well, now, I also want to point out that pieces of this presentation, I mean, this is all compiled by me and from my own head, but a lot of this came, like, this isn't all stuff I invented myself. Definitely not. A lot of this actually comes from other members of the community. So I just wanted to call out these particular people, and I apologies if I missed anyone, but we've got Ben Karcher, Grace Fu, Philip Newman, Ryakusha, Sai, and Varedos, who, at least from my memory, definitely contributed a lot of really cool ideas and implementations and other solvers to the community. All right. So, who is this presentation for? Fans of variant Sudoku. I'm assuming you know a little bit, at least, about what variant Sudoku is about and why it adds complexity to computer solvers. You do not need coding experience at all. I'm not really going to talk a whole lot about like detailed coding stuff, but more high level concepts that I'm hoping you can understand. And if you're just curious about how a solver thinks about stuff, this is the presentation for you. Have there been any questions about any of this so far, or any commentary?
Not so far. I think the
Okay,
most
great.
common thread is, what is a Sudoku solver? Is it a bot that solves a Sudoku puzzle on its own? And that was Cool Dude Gaming 123.
Yeah. So to give a little bit more context, it is a computer program that is used to explore the solution space of variant Sudoku. So, or just a classic Sudoku if you'd like. It definitely supports that, and it's intended to be used by setters during their setting process. So it can be used to validate that the Sudoku has a solution. It can be used to validate that the Sudoku has only one solution. It can be used to explore possibilities so that the solver knows, hey, here's maybe a direction I might want to go. So that's a really high level idea, but that's the concept, because often when you're setting a variant Sudoku, especially with certain constraints, but just all the time, you're going to run into situations where you've broken the puzzle and there aren't any solutions yet, and you just keep building because you haven't realized that. And so what my solver does is it kind of acts as kind of an assistant saying, hey, here's kind of the technicalities of what's going on with your puzzle right now, and where you might want to explore. What it doesn't do is tell you whether it's a good puzzle, and what it doesn't do is tell you whether a human can solve it. It does some attempts towards the second, but nothing for the first. All right, hopefully that answers your question. So, what are you going to learn today? How a solver tries choices, how a solver makes safe moves so that it's correct, how it understands the grid. So, we're going to go over how does this computer program actually understand and encode the grid itself. How does it enforce rules on that grid? And what's making it fast, because it's very easy to make a slow one. It's very hard to make a fast one. All right. What you're not going to learn, low level details. There's not going to be code on screen. There'll be some technical stuff, but I'm going to try to make it as accessible as possible. You're not going to learn how to code, and you're not going to learn specifics about particular languages. So I'm not going to be focusing like on C# or Rust or excuse me, JavaScript, except there's going to be one slide that mentions them for those who might be exploring creating their own solver. But that's just a really quick tip. But that's all that's going to be there, and you're happy to ignore that. All right. So what I'm going to say is that my solver has the fast solver and the logical / human like solver. So first, let's talk about how does the fast solver work. So the point of the fast solver is to do it is to get you answers about your puzzle that don't have to do with how a human might solve it. It's about exploring the space of the puzzle, and it needs to do that as quickly as possible. So it's not telling you how it got that answer. It's telling you, hey, this is the exact correct solution space right now. So the first thing we need to do is quick, basic logic. You don't want to go too far with this. In fact, you don't want to go almost anywhere with this. But there are some really basic things you can do, such as finding singles. So if there's any singles on the grid, that's going to be naked singles, which is where a cell has only one possible value left. It's going to find those and apply those. And then also hidden singles, where within a region that must have all values, if there's only one place for that value, it's going to find that and place that. But that's about it. That's all the basic logic that's actually implemented within the fast solver. Now, this can actually solve some puzzles. All the New York Times easies can be solved with those two techniques, but those also aren't the interesting puzzles. So we need to do more beyond that to make sure that we have a exact, correct exploration of the space. So it's going to get stuck. It might not even do anything. during that basic logic. So then it's going to try something. So there's going to be some number of possible choices to make. Like it's going to maybe find a certain cell and it's going to see that cell could be a 1, 2, or 3. And it's just going to say, hey, let me try 1. Some might call that bifurcation if a human solver were to do it. Now, there are heuristics towards which one to pick. And my advice for which one to pick is find the thing that is the most constrained, that has the fewest choices to it. So, one of the most obvious ways to do that is to find the cell with the fewest candidates remaining, preferably a bi value, meaning there's like maybe it only has 1 and 2 as an option, or 3 and 5, and then pick one of those. You can get smarter about it, but be careful that you're not trying to be so smart that it takes a long time to find the choice, because that's going to slow you down. All right. So once we've made that choice, before we make the choice, we're at state A. This is just whatever the grid looks like at this point where we got stuck. So we're starting with a state. We're going to call it state A. Now, B is going to be our choice, and we're going to set B to true. So that's going to create state A plus B. So we've basically just said, make a guess. If this cell could be 1 or 2, we're just going to fill 1 into it, and we're just going to create that state. But we're going to keep state A around. So we need to copy state A and then apply B to it. Now, so basically we're guessing if B is true, but we're always able to backtrack back to state A if we need to. Then we're going to do this quick basic logic again. So if I guess that there's a 1 there, that's a single on its own. It's going to, populate with more restrictions across the grid, and then that might create more singles, and so that can cascade. It might even solve the puzzle. So in that case, there's 2 possible options after doing so. One is that the grid is still valid. As far as we can tell, it's still valid. Now, that validity check is also important. You want to try to catch as many issues with the grid early as you can, but you need it to be really fast stuff. So generally, I build that into the single finder. So for example, while it's looking for naked singles, it's also going to be looking for any cells that have no options in them. If a cell has no options, then that's an invalid grid. It can also look for, when doing the hidden single check, where it's looking at each row, at each column, at each box, for example. It might find that there are 0 places to place a particular digit. If that happens, then the grid is invalid. So there's basically just this validity check that it goes through. And if it finds, hey, as far as I can tell, the grid is still valid, then it's going to repeat that process. Basically, state A plus B becomes state A. And assuming it's not solved, it's going to try another guess on that. But we're building up a stack here. We're still remembering A plus B, and we're still remembering A. So what if it appears invalid? If we go, what we did here didn't actually work. It created an invalid grid. That means that this cannot lead to a solution. That means that B cannot be true. So instead of repeating with A plus B, we repeat with A minus B. So if that cell had 1 or 3 available, and we tried 1 and reached an invalid state, then now we know that 1 can't be true, so we can set 3 in there and repeat with that. Or if it was 1, 2, or 3, and we found that 1 is not valid, then we repeat it with only 2 and 3 as options. And so probably then it's going to guess 2 and move on. But even just eliminating that 1, maybe that creates a hidden single or something like that, where it can propagate basics. So we repeat that with state A minus B, where we're going to do all the basic logic to it, make a guess, see if it's valid, invalid, etc. So even down here, if A plus B eventually finds that it's invalid and it cannot create a valid grid, then it's still going to pop all the way back up here and try state A minus B. So no matter what happens, whether we find that the state is valid or invalid, we've made progress towards finding a solution. So to cap this all off, this is a tree, and it can be visualized as a tree. This is what mathematicians would call a tree, where for some reason the root of the tree is at the top. But we start with state A, and then there's 2 branching possibilities from state A. There's the A plus B possibility and the A minus B possibility. Then from the state A plus B, there's the A plus B plus C and the A plus B minus C. And from A minus B, there's the A minus B plus C and the A minus B minus C. So you can see how you can sort of build out a tree of choices where is this thing true or is this thing false? And you're doing a kind of a binary branch from each state. And so you could potentially populate all of the states that are possible for the grid. So that is the basic concept of the fast solver. This would be a great time if there are any questions or commentary.
I guess I have a question of my own. Hopefully,
Yeah.
my volume is okay for people in the chat. I know it was a bit loud and then a bit soft. So, I guess as I'm hearing you talking, I'm thinking of like, Deep Blue and some of like the chess solving computers that they had and such. Is it a similar kind of thing with that? Except I guess maybe in this sense, maybe a little more simplified in that you're looking at numbers as opposed to pieces moving in different positions. But is it the same kind of same basic sort of functionality?
So I'd say the biggest difference between something like this and something like a chess engine is that chess engines don't know what the opposing player is going to do. So it's not full information.
Okay.
So chess engines are harder, definitely harder, because they need to make assumptions about what the other player is most likely to do, and that explodes the solution space.
Okay. So it's a
So
much bigger, I guess, data set that they have to figure out.
yeah, it's a
And
bigger search and there's a lot more heuristics involved. Here, the only heuristic is I have to make a guess. Which guess should I make? That's a
mm,
heuristic, but everything else is very much just purely logical and it can do it extremely quickly.
yeah.
So I'd say
Okay.
that's the big difference. A single player game versus you have an opponent who you don't know how they would specifically react to a
Right.
move.
I guess in a sense you're playing against the puzzle which has defined things that it can do rather than, like you say, an independent player.
Yeah.
Okay.
Now, I would say that if you were trying to make a solver that solved fog, you definitely have to try to account for that. But I don't think that that would be viable, to be honest,
Yeah.
because you don't know what's behind the fog. But if there were like really specific rules about what the fog could do, maybe. But that might be kind of a good analog if you're trying to associate it with Sudoku. And you can see why
Yeah.
that would make it much more difficult to explore the space. And it could not give you exactly correct answers.
Right. Right. I guess unless it had something like defined parameters as there could only be arrows behind the fog as opposed to any other possible constraint.
Yeah. But
Yeah.
still then, the solution space that it explores is gonna involve errors that don't actually exist behind the fog, right?
Right.
Just
Right.
like a chess
Exactly.
engine's gonna explore moves that the opponent ends up not making.
Yeah. Yeah. Okay. Cool. And yeah, just to add on, as Rang said, if you have questions as Rangs is talking, please throw them in the chat, and then when there's a natural kind of pause, then I will ask them on your behalf. So, okay.
Well, I'm gonna move on. There's still plenty to talk about.
Yep, sounds good.
So, what is the fast solver used for? What does it do? So, the most basic function, which is still very useful, is to find a single solution. So what it's going to do is it's going to traverse that tree in the way that I described earlier until it finds a solution. Then it's going to stop and it's going to say, "Hey, here's a solution for you," and it can do so in a deterministic way, so that it always returns the same solution. Now that solution is still going to be somewhat random, but every time you call it on the same grid, it'll give you the same solution back because it's going to explore based on its rigid heuristic. So it's going to give you kind of the first solution it finds that way. Or you can introduce random traversal, where when it goes to make a choice, there's some randomness involved in what choice it makes. So, for example, if it identifies, hey, I want to try this cell that's a one or a three, in the deterministic one, it's always going to pick the one first, and then it's going to try the three if the one didn't work. Whereas with random traversal, it's going to flip a coin and say, well, do I try the one or the three? Let's coin flip and see which one to try. And that only makes a difference if both a one and a three could lead to a solution. So what's interesting about this is only something that the random solution is only something that you need if there is more than one solution to the Sudoku. And when you look at a lot of classic Sudoku solvers, they're most interested in Sudokus, or really a lot of them only support Sudokus that are already unique, that only have one solution. So they don't even worry about that. But my tool is intended for setters as they set. And it's only when you reach near the end of the setting process that there's only one solution left. And so my solver is designed to be able to explore that space in different ways, even when there are many solutions remaining. Um, the next thing it can do is it can find or count all of the solutions. Finding all the solutions would involve outputting them all in some way, whereas counting is faster because it can just throw out the solutions as it reaches them. So what it's going to do is it's going to go through the tree, and when it finds a solution, instead of exiting, it's just going to like increase that counter, maybe store off that solution somewhere if you want it, and then it's going to continue as if that was an invalid grid. It's going to backtrack back and say, "Hey, that decision wasn't good," as if it was invalid, and then it's going to continue from there, exploring the tree. Um, this is something that's really important to be able to count a large number of solutions. And actually, a lot of solvers don't build in that support because they only expect one solution. And so, what you end up having to do is something very slow, which is it finds a solution, you then start over and ban that solution saying, hey, that isn't a like you basically add another rule saying this solution is no longer possible, and so then it would come up as invalid. But in the solvers that I write, there's always a way to just continue the tree instead of starting over, and so that very quickly count all the solutions. All right. The other thing it can do is check if the grid is valid or unique. And actually, that's just calling the solution count, but you want to be able to pass a cap into the solution count. So, hey, when you reach some number of solutions, stop even if there's more or potentially more. And so what you do is you just set that cap at 2. And if it returns that there's 0 solutions, that means it explored the entire space and didn't find any. So your puzzle's invalid. There's not going to be a solution to it. If it returns 1, then you know that it didn't find a second one. So there has to be only one solution. It explored the entire space and only found one. So you're unique. And if it finds 2, that means there's at least 2 solutions. So you're not unique. That means you need to add more rules in order for there to be only one solution. Any questions or comments about those? I think those are kind of the pretty often used functionality, while setting
Mhm.
at least.
No, not seeing anything. So
Okay.
sounds good to me.
Um, Now this is the one that you mentioned earlier, Tallcat. It's actually as I don't inventing is a loaded word, but I came up with this myself without having heard of it happening before. There probably, I mean, I'm sure that it's not completely unique to me, but this is something where by approaching wanting the solver to be useful to setters, and me being a setter myself, I said, "Hey, this is something that's going to be really useful to me," and I really needed it for a puzzle I was working on, and so that's why I implemented it. And it ends up being the most popular feature of my solver, and tons of setters use it. Some setters avoid it because it's not their style, but um, that is the true candidates. So the concept, and this isn't the implementation, this is the concept, is that we want to find all the solutions to the puzzle and then union them together. So if there's one solution with a 1 in the first cell, and then there's another solution with a 2 in the first cell, then that means that 1 and 2 are possible in that first cell. But if there are no solutions that have a 3 in the first cell, then 3 is omitted as an option in the first cell when displaying. And so what that means is if you tried to set that to 3, we immediately know that that excludes all solutions, so your puzzle is now invalid. So what I can do is I can calculate these true candidates, display them, and as you make changes to the puzzle, I update that in real time as quickly as it can, and it is very snappy for most puzzles. Um, and so then as you set it, you can immediately know, hey, are there no solutions to this puzzle, or am I restricting things, or is this constraint that I add or a given that I add, is that going to break the puzzle, or is that going to limit the puzzle? The other thing it can do is it can report how many solutions existed for that candidate. So maybe the 1 was present in 10 different solutions, but then the 3 was present in only one solution. It can color code that. And so then you know, oh, if I set this to 3, I will now have a unique solution. And that's really useful, especially towards the end of the puzzle where you're just trying to make the puzzle unique. You can really lead you towards, hey, this one's a much more strong candidate to set. If I set this other one, then I'm still gonna have to add even more rules in order to get to a unique solution. And I guess I should emphasize that having unique solution is a necessary requirement to publishing a puzzle, because in order for a puzzle to be logically solvable, it has to have only one solution. And so all valid Sudokus, including variant Sudokus, have only one solution. Now, reaching only one solution does not mean you can publish it. It's just a requirement. It's necessary but not sufficient. Now, there is no way that, especially like, let's say we had a blank Sudoku grid. You first open up F puzzles, it's a completely blank classic Sudoku grid. Um, there are way too many solutions to that for us to find them all and do a union. Now, we know that the union is just 1 to 9 in every cell. So clearly, there should be some way to reach that without finding all solutions. And so the way that this is done in my the latest kind of tech for this is a tree pruning method. So remember that if I go back to here, the entire exploration of states is a tree. And so what I can do is, as I explore that tree and find solutions, I could update the union of solutions to say, okay, here's the candidates that are possible in every cell according to all the solutions I found so far. And if I get to say state A minus B here, and I look and I see that state A minus B is a subset of the solutions I found so far, as in there is no additional candidate within that state that I haven't already found as being possible in the solution space, then I can trim this and not explore it, because the only solutions I will find will be ones that cannot improve my idea of what candidates are possible in a cell. And so at the beginning, you're finding a bunch of solutions and you're unioning those solutions into that bucket of unions. But then at some point, you start just trimming large parts of the tree, and you end up just zipping through the rest of the tree because most of it gets trimmed, and then you can return the result. And so this is an extremely fast way without having to repeat any work to, as I put here, you skip branches with no new information. Now, what's important here that I discovered when implementing this is, especially with certain variants, it's important to perform a little bit of extra logic every once in a while to assist with the pruning. So, for example, if there's a naked triple in a row, then the rest of that row shouldn't have those three values in it. But if you don't actually find that naked triple and apply it, then there's going to be a large amount of solution space that tries that those triple values in cells where, if we knew about that triple, we would know not to try those. So it's not going to find any solutions in those, but it's not going to be able to trim them because those cells have those extra candidates that haven't appeared in the solution space yet, because they will never appear in the solution space. So you want to be very careful about how often you do it, but you want to implement some extra logic like finding pairs and triples, even finding stuff like fish. I don't remember exactly what I settled on. I'd have to reference the code, but I did a lot of timing and testing of what logic to include and how often to do it in order to make this much snappier. So if you do kind of just the implementation that does singles only all the time, then it's going to be very slow, because you're going to have a much larger solution space to explore because you can't trim those trees early. All right. I feel like I just presented something a little bit complicated. So if you have
Yeah,
questions about that, even Tallcat or the chat.
and just so Rockrat actually had a comment of true candidates is like Doctor Strange. I saw 14,065,000 solutions. How many had a 5 in row 5, column 5? One.
Yeah.
But no, I was going to talk a little about, so I mean, I was using true candidates earlier, and it's very. I personally tend to try to use it sparingly because I think it's a very powerful tool. Um, I tend to mostly use it when I'm concerned that something I'm going to do is going to break, and I think it's great because of the thing of you put a clue in and it automatically just goes X X X X X. It's like, okay, great, I'm not wasting my time. And I had that happen a couple of times earlier. Um, I guess in that sense, do you feel, and this is not so much a technical question as maybe a vibes question and such, do you feel in some ways that there are other sellers out there that kind of maybe use it a bit too liberally, and they strive to get the unique solution, and then they say okay, and they don't actually do the test of is it humanable or
Yes, exactly. I can definitely talk about that. I have a lot of opinions
not. No,
related to
opinions are good.
that.
I like
Um,
opinions.
and I don't know. Hopefully you aren't surprised to learn that I generally agree with you and don't encourage the complete use of this feature. It is a very powerful feature, but it can also act as a crutch, especially to inexperienced setters.
Mm,
Um, Basically, the way I would put it is it makes it really easy to accidentally make a computer generated puzzle.
hmm
And no one wants to play computer generated Sudoku variants. They want the logic to be intentional. And so the way that I use True Candidates is I do have it on all the time, but if I can't figure out why a candidate was eliminated, then I pretend it wasn't.
mm,
But I still keep that in mind when setting, right? While I'm setting, I know not to set it to true because that'll break my puzzle immediately. But I also, if I can't, like sometimes there'll be a surprise. Often, not sometimes, often there'll be a surprising elimination, and I'll be like, why did that thing over there get eliminated? And that can trigger me to go, well, let me explore that. Let me figure out what the logic is. Like even just like open this thing up in Sudoku Pad and just like solve from here and see if I can figure out why that got eliminated. If I can figure it out and I think it's fair and I'm like, ooh, that's a cool step, then what I can do is go, ooh, what if I can reward the solver for finding that deduction?
mm,
But if it feels unfair or I can't figure it out at all on my own, then I just pretend that elimination didn't happen when I'm thinking about where do I want this puzzle to progress.
yeah.
So you kind of have to keep that in your head, and you can. Uh, I find actually kind of useful is using the given candidate feature where
Mm,
you can type in those red candidates underneath the black ones. I'll use that to kind of notate where I think that cell is in a fair way, even if I'm add to basically to add extra candidates to it because I know true candidates is going to override anything I do otherwise.
yeah.
So
Yeah. Yeah.
that's kind of how I use the feature.
Yeah, it is. It's very. I mean, it's similar to me. I think very handy for figuring out breaking. Today, I used it because I was like, I have a 15-minute segment to set a puzzle, and I'm just going to throw everything in. And honestly, I'm actually going to go back and look at the puzzle, and it's probably not going to be solvable at all. But yeah, I guess so. To some degree, though, there's a caution, and not just. I mean, the F puzzles and the true candidates. I think I would agree with what you said about it being perhaps one of the most powerful and popular out there, but I think that goes for some of the other solvers as well. The, what is it? By the man with great power comes great responsibility, and I think you have to be judicious in your use of the tools as well.
Yeah, and I think another aspect of this that I want to touch on is a lot of new people who haven't set any puzzles yet and they want to get into setting. It's actually surprisingly common for them. I don't know, maybe it's not surprisingly. It's very common for them to say, you know, setting a classic is hard. Setting something with really weak constraints, that's probably hard too because they don't know. So I'm going to set a puzzle that has a very strong constraint, and often they gravitate towards, say, anti-knight. They're like, I'm going to set an anti-knight puzzle because that's really powerful and a global constraint, and I think that's fun. A lot of anti-knight puzzles I've solved, I've had fun solving. So I'm going to set an anti-knight puzzle. And then they go and try to set it, and then they never succeed, and then they give up on setting because actually setting an anti-knight puzzle is extremely difficult.
Mm-hmm.
The way to think about this is a blank Sudoku board has, I have the exact number somewhere on my slides, but it doesn't matter. It's somewhere on the order of 10 to the 26 possible solutions to a blank Sudoku board. A blank anti knight grid has, if I recall correctly, 11 million solutions. So just by turning on anti knight, you've gone from 10 to the 26 down to 11 million. And so now you have such a small solution space and such surprising uh, such a surprisingly I guess the way I should put it is um, changing one thing can often affect large swaths of the grid. If you're doing that kind of just at random and trying to figure it out, um, you're gonna end up breaking the puzzle, and then you're going to spend an hour adding more clues to an already broken puzzle because by your own logic you haven't found those things. And so I almost think it's essential to have something like the true candidates feature to set an anti-night puzzle,
Mm,
because you're going to get those X's across the screen with almost everything you do, especially near the end of the puzzle.
yeah.
And you won't necessarily know why. Now, you still need a lot of experience and good setting uh, uh, ability, or ability isn't the word I was looking for, but instinct, in order to
Mm,
set a fun anti-night puzzle. But if you're going to set one that's possible at all, I think you do need true candidates, unless you're a super setter.
yeah,
I know
absolutely.
people did set anti-night puzzles before my tool existed, but I think my tool maybe caused an explosion of that kind of puzzle.
Yeah, I think it's funny you mention anti-night because I'm probably the one person here who's like, God, anti-night. But I think anti-night is one of those constraints where for me, and I have actually set an anti-night, which I've never published. It was actually after the gas stream I did
Mhm.
with Sudoku and Philip, and Sudoku had thrown like an anti-night opening in. And I was like, you know what? I'm just going to set it. And I set it and it's on my computer and it will probably never get published because someone somewhere is going to hold me to the fact I said I would never set an anti-night. But I just feel anti-night is one of those constraints that you just don't have good control over, that you set a couple of things and then it's like the constraint takes it out of your hands, which I think is where the solver comes in clutch for that.
Yeah, what your experience is exactly right. Like, you think you've just started setting the puzzle, and the solver says it's unique or broken, right? And
Yeah.
you're like, how am I supposed to be creative within this space? And I think I think there's kind of, I don't know, there's the advice of like, if you're too constrained, it's difficult to be creative. But also,
Mm.
if you're not constrained enough, it's difficult to be creative. So you
Right.
want to find that sweet spot. And I do think that anti night is way too restricted
Yeah.
to have a huge amount of creativity in it.
Yeah.
All right.
All right.
This next slide is something that a lot of people won't know about, but it is a new feature in the solver available now. It has been available for a while, but you can estimate the solution count now. So, why would you want to estimate the solution count? Well, it's mostly a solution in the search of of a problem, but it's very cool, and it can answer some theory questions that we couldn't answer before. So let me give you one theory question that we did not know the answer to. I implemented this, and then we did know the answer to. But you can also see why it's like, okay. So the question was: does Sudoku X or Anti King have more solutions? If you had to guess, which one would you say?
Um, which has more solutions?
Yeah.
I would say I would say Sudoku X has more solutions, I
Okay.
guess.
Now, all kind of attempts at exploring this before this feature made them seem like they were extremely close in number of solutions, and no one could. But they both had too many solutions to get the exact count, so there was no way to quite know the answer. Now, what this is it uses Monte Carlo methods. Now, Carlo has existed since the 70s. Um, but it's named after Monte Carlo, where a lot of gambling happens because you're essentially gambling. But I first learned about it with path tracing when I implemented some ideas from path tracing into a something for work. And with path tracing, the idea is you need to be able to shoot rays all over the place, all over the scene, but you can't just shoot all of them. You want to be able to shoot some of them and then make inferences about what the whole scene looks like based on that. And so basically, you're trying to solve this spherical integral and with no closed solution. And so, in order to solve that spherical integral, you use Monte Carlo. And so, I learned it from that, and I was like, I don't even know if it was me. I think it was a discussion. And again, a lot of this I listed names earlier, but the basic concept is that we apply this complicated Monte Carlo technique to explore the search space and come up with an estimate of how many solutions there are. And so what we do is we just start from the top and just take a random path. And that random path might come up invalid or it might come up with a solution. And we account for the probability that that path would be taken. And we repeat that a bunch of times and then do the Monte Carlo math that all the textbooks tell you to do, basically. And it spits out a kind of range, kind of like an estimated solution count and then a confidence range. And so we generally use the 95% confidence range. So with only 10,000 iterations, which is not very many, a blank 9 by 9 classic, my solver tells you that there are 6.49 times 10 to the 21 to 6.84 times 10 to the 21 solutions. If you were to take that average, it would be 6.67. Well, we know the actual number because some crazy people did it over a few years. Uh, and the actual number of solutions is 6.67 times 10 to the 21. So, in a matter of seconds, the Monte Carlo came up with basically the correct answer. And at the very least, you get better than an order of magnitude. We know it's somewhere in the 6 times 10 to the 21 range. So, does knowing the exact count, is that helpful? And this actually extends out that they have the exact, but is it is that necessarily more helpful than knowing the range? I don't know. What are you applying it to, right? It's just kind of like we wanted to know the answer. Okay, now we do. Now, anti-king, no one had ever bothered to spend the years and tons of CPU resources to count anti-king and also to count Sudoku X. And so we can do the estimations, and anti-king has about 5 times 10 to the 17 solutions, according to 10,000 iterations Monte Carlo. And you can do more and more iterations, and it just increases the confidence. And so, as it turns out, anti-king has about 10 times as many solutions as Sudoku X. So Sudoku X, I believe, is in the 10 to 16 area. Um, I did not actually look at my notes on what the Sudoku X result was, but I do believe from memory that that's what that was. So being within a 10x, like that's hard when there's this many solutions to like really nail down which has more. But now we can answer that question. Yeah, and so you did guess wrong. It's interesting though, like because they both restrict the grid inside a kind of a global way, but not in a way that's easily comparable. All right. So, any questions about this or commentary before we move on?
I am not seeing any in the chat, but yeah, I totally guessed wrong. I guess, yeah, anti-king and so as an example, if you, I mean, going back to anti-knight, if you plugged anti-knight in, do you have an idea of what that would kind of come out with
Yeah,
relative?
I've actually done the exact count of an anti-knight because it's only around 11 million,
Oh,
and
oh,
so it
quite
does spit
so.
out the correct answer for
Not
that
even
too.
like, yeah,
Yeah,
wow, that's a lot.
and
Goodness.
non-consecutive is about 8 million. I'm doing this off the top of my head, so I'm sorry if the numbers are a little off, but I'm getting the orders of magnitude right.
Yeah, yeah,
Um,
goodness. Okay.
Now, what's interesting is the Monte Carlo estimator can also kind of tell you whether your constraint is volatile. So for something like
Mm,
classic Sudoku, anti-king, Sudoku X, it really very quickly narrows down the range and has a high confidence. If you do this for non-consecutive, it has a lot of trouble. It bounces around. The confidence gets worse and better. It'll have like a very poor confidence for quite a long time.
mm,
And that's partially because the solution space is small. But I also this is kind of my hypothesis, is that if you've ever tried to set non-consecutive, you'll notice, especially with true candidates on, you'll notice really random stuff happening in completely unrelated places of the grid as you add constraints. Like I call it spooky action at a distance after quantum mechanics, where it's like I'm working up on the top left corner, and as I do that, for some reason the bottom right corner is getting eliminations, and I can't figure out why, and no one can figure out why, but it happens. And so
yeah.
I think that the non-locality of non-consecutive causes the Monte Carlo technique to have a hard time converging on the correct answer.
Mm, mm. I mean, I remember when you gave your talk at SudokuCon in April, and actually, there's a bit of it that I think is just hilarious when you were saying, "Oh, I plug this in, I plug this in, you can see all this random stuff disappears, but it's anti-night, so of course,
Yeah.
yeah, right. Yeah, so I mean, you kind of pretty much answered, I think, what Palfly was getting at. So you mentioned non-con. Have you done any thoughts on, like, say, disjoint or entropy slash modularity? Or
Um,
they
I
they
don't have if you're talking about global entropy, I actually
yeah.
don't have that implemented in my solver. It's actually not an easy thing to implement. And I'm actually gonna go over later, how constraints are implemented.
Mm.
Hopefully we have time to get through everything.
No, I think so.
We still have like 50 minutes, right?
Oh, we have like an hour, I think. Yeah, we're good.
Yeah, an hour. Okay. I'm gonna go over like what constraints are easy and what constraints are hard and why. So that might help with that. But I haven't really explored those myself. But the solver is publicly available, and this feature is so.
Yeah.
Try stuff out. Hit the estimate button on NF Puzzles and see what it says.
Paulfly, looks like you have some homework. All right, continue.
Alrighty. So I'm not going to focus too much on the human solver because honestly, I find it less interesting. But I do want to talk about why it's less interesting and kind of how it gets implemented and the huge struggles that are a part of it. So this is the only slide for the human solver. I call it the logical solver within the code base. Now, the purpose of this is people are don't want to just know even when you're setting the setter doesn't want to just know hey these things are possible. They want to know why, and the human solver attempts to tell you why in a way that mimics how a human would arrive at that conclusion. And what that ends up looking like is hand implementing as many techniques as I can essentially. So like you've got, naked single, hidden single, but special implementations of them where it's gonna um report one at a time and it's gonna say, where it is and all that. You're gonna have pairs and triples and quads and all that stuff. You're gonna have X wings and fish like swordfish, jellyfish. You're gonna have um wings, all the various kinds of wings, like Y wing and W wing and all these other wings. And then you're going to have alternating inference chains, and you're going to have blah blah blah. You're going to have set like deductions, right? You can think of all these different things that you might implement that a human solver might use, and you just hand implement all those one at a time, and you have to test them thoroughly. Um, and then, at least what my solver does, is it comes up with just I basically not my solver, but I put into the solver a heuristic order to what seems to be the simplest deduction found. So, for example, a naked single is going to be considered easier than a pair. A pair is going to be considered easier than an X-wing, right? That kind of thing. Even a pair is easier than a triple. And so what it's going to do is it's going to kind of look for singles. Then it's going to look for pairs and triples and stuff. Then it's going to look for pointing and claiming. Then it's going to look for X wings. Then it's going to look for swordfish, etc. All the way down until, either it finds something, in which case it reports it, or it doesn't find anything, in which case it says, I don't know. So that's the basic concept. So we have that heuristic order. Now, that what's interesting about that is something I've noticed, yeah, as a solver myself, is not all naked singles are created equal, right? There are some that are extremely easy to find, and some that just kind of hide away somewhere where it's really non-obvious, unless you're, a pro solver who's really practiced at finding those. But a computer can't tell the difference. All it knows is, hey, there's this cell with only one option, so there you go, naked single. Um, so sometimes you might actually find there's this obvious pair here and a non-obvious naked single. A human's going to find that pair first, but the solver's always going to find the naked single first. um, and so it also means that it can't solve all puzzles. So true candidates might tell you, hey, this particular candidate's not possible, but then you run the logical solver and it doesn't know how to eliminate it, and it doesn't. So that is definitely a problem. And there are puzzles with no known techniques to solve them unless you have this thing called dynamic chains, which sometimes would take 100. If you were to print out the instructions on how that dynamic chain works, you would need 100 pieces of paper to print it all out. And so, is that really human at that point? And then also, I get this complaint all the time. It missed this obvious thing. Like, hey, I have these two killer cages, and it's obvious that they interact in this way that every human's going to see. But my solver treats that killer cage as one thing and that other killer cage as another thing, and it doesn't see how they interact, and it misses that. And so what I tell them is, okay, cool, put that in there, restrict the candidates yourself, um, or use the brute force solver, the fast solver, and it'll find that. So yeah, and certain constraints are notorious for it not finding the correct logic for that, when it's should be obvious to a human who's used to that constraint. I will mention that there is kind of an enhancement to true candidates that I have in my solver, which is you can pick a set of logical steps and you can have it display candidates that true candidates have eliminated, so aren't actually possible, but the logical solver is not able to eliminate. And that can be useful to preserve break-ins. So you have some initial thing where you're like, this break-in eliminates this stuff. And I want to make sure that as I finish the puzzle, that at least this set of techniques won't also eliminate that stuff, thus bypassing my break-in. And so you want to keep those candidates visible. They show up in red, um, throughout the entire setting process, um, so that there is no, some clue you add near the end to make it unique. Oops, that accidentally completely bypassed the entire puzzle and made it trivial, right? You don't want that to happen, and so that can help you with that. Especially in classic Sudoku, I've utilized that to set a classic Sudoku where I have a particular technique that I want to preserve. Like, hey, I want to make sure that you need this swordfish, but then you finish setting the puzzle and it's all singles. Oh, where'd my swordfish go? All right, it seems like there's been some comments. So you want to summarize for me?
Sure, yeah. I mean, Marog kind of commented and said the concept of quote unquote obviousness is hard to codify. I mean, it's
Yeah,
true. Like, oh, what's obvious is such a thing. Juggler mentioned if a really well implemented logical solver can't rule something out, even though a brute force solver can, it sometimes it's a good signal that the puzzle will not be fun for humans. But other times there's a quote unquote clever trick that humans are better suited to find than the logical solver. Um, I remember, CTC, and they occasionally still do it. They had their thing of occasionally putting classics up and saying, well, we plugged it into a computer solver. And, I think Shai had a few of those, and it was trying to showcase a new technique of some kind of how I guess a human could outlogic a computer in a way, but it's kind of
yeah,
on the flip
exactly.
side.
Yeah. And what I'd say is if you encounter that as a setter, you can just eliminate candidates yourself and the
Right.
logical solver will respect that elimination. So you can say, okay, it gets stuck here, but there's this kind of thing that I'd expect a human to find. So I'm going to just apply that, and then now I can continue the logical solve, from there and see if is that step the only thing or does it get stuck again. I would say that unfortunately I have yet to encounter a logical solver where it correlates at all very well with whether a human has trouble.
Mm.
um, one aspect that I'd like to explore with that, which I haven't had the opportunity to, so maybe someone else will. Feel free to take this idea. And I think Sam Kappelman-Lyons has actually implemented something along these lines and explored it as well, which is bottlenecks.
Mm.
So I solve the New York Times hard Sudoku every single day and make a video about it and get a lot of comments about whether people struggled or not. And so I have a huge amount of data kind of just, in my head. Like my brain has heuristically come up with some patterns there. Whether or not they're true is something to explore. But the idea is which puzzles, because all of these puzzles only require a small set of techniques. You need basically what I would say is you need singles, you need lock candidates, and you need lock sets. That's it,
Hmm.
to solve every single puzzle. So according to a computer solver, they're all going to be about level of difficulty because they're going to be like, well, these techniques were needed, so it's this difficulty. Um, but that's certainly not the case for humans. Some puzzles, people are like, "Oh yeah, I solved that super quick. It almost felt like the easy." And other puzzles, people are like, "This is the hardest one I've had to solve in a year." When they all just need the same set of techniques. And what I found is it often involves some kind of bottleneck. What I mean by bottleneck is like, how many things can you find right now that match that list of techniques.
Mm.
If it's 10 things you can find, 20 things you can find, the chances are you're just going to randomly find one of them as you search through the grid, and then
Mm.
you'll make progress. If there's only one thing to find, then you have to find that one thing, even if it's a naked single, even if it's supposed to be an easy thing. If you miss it and there's nothing else in the grid that could give you progress, you could get stuck on that for half an hour, because you just don't see it.
Yeah.
You might even restart the puzzle at that point and
Yeah.
hope that you
Yeah.
see it the second time around. And so that made it hard, right? So I think that true analysis of difficulty should account for bottlenecks, which mine does not.
Mm.
But it would mean being able to enumerate, here's all the possible steps at this point, um, and trying to sort of explore the step space, kind of in the same way that we explore, the fast solver explores the solution space. We would explore what steps are possible, what order would we apply them in, and is there a certain step that seems to be always required?
Mm.
And if so, how hard is that step to find? And that can kind of determine the difficulty.
Yeah. And I think for me, and I keep bringing it up, it's probably why I dislike anti-night puzzles, because I think more often than not in those, there are those things where it's like you have to spot that one cell that just so happens to see every single digit, most of them by anti-night. And if you don't get that, then you don't get progress.
Yeah.
Yeah.
And I will say a lot of classics are actually set kind of to create a bottleneck on purpose in
Mm.
order to showcase a particular technique.
Right.
And so, obviously they wouldn't need that technique or be difficult if it was bypassable.
Yeah.
And so I would definitely call that a bottleneck. Like
Mm.
if Shy is showing off firework, right? You have to apply the firework or there's just nothing to do. And so
Right.
if you put it into a computer solver that doesn't know how to do firework, you're going to be able to rant and rave about how it does the 3D Medusa and then guesses
Yeah.
in order
Yeah.
to solve
Yeah.
the puzzle.
Yeah. I guess it's the
Um,
whole thing of like the concept of the one stepper, that you get that one step
yeah,
and then it collapses. But
exactly.
yeah, anyhow, I'll let you carry on.
All right, so that's all I'm going to talk about with regard to the human solver, other than maybe a few things when we talk about constraints, but that's kind of the focus there. All right, so now into some of the more meat and potatoes of the solver, representing the grid. How do we actually take a visual Sudoku puzzle and put that into the solver in a way the computer understands and does so quickly? And so the first thing that I kind of want to talk about is that an individual cell is a single integer. And this isn't the only way to do it, but this is my recommendations. And this is how I generally implement it. Um, and this will make it fast. So, what do I mean by that? Well, let's say we just have a cell in the grid, and 1 through 9 are the possibilities in that cell. Now, no, integers are more than 10 bits, but we only care about 10 bits in this case. So, we're going to need if it's a 9 by 9, we're going to need 9 plus 1 bits. If it's a 6 by 6, we need 6 plus 1 bits. So I'm going to assume we're talking about 9 by 9 right now, but it is flexible. Um, yeah, depending on the size of your integer. So if you're using a 32-bit integer, you can do a 31 by 31 at maximum. If you have a 64-bit integer, you can do a 63 by 63. Most people do 9 by 9 and smaller though. So this is how integers are represented in a computer. It's actually in binary. And so you've got ones and zeros that are kind of a string of ones and zeros. In this case, I have 10 of them. And so what I've done is I've said, okay, if the one is a possibility in the cell, then this first bit it is set to one. If the 2 is a possibility in a cell, then this second bit is set to 1. So this is whether 1 is possible. This is whether 2 is possible. This is whether 3 is possible. And we when we talk about integers, we always go right to left, because if you think about writing the number 123, the 3 represents kind of the smallest thing and the 1 represents the 100, this biggest thing, right? And it's the same in binary. And then we have this extra bit at the end, which I'll talk about, which is whether or not the value has been propagated. And that's kind of an internal kind of scratch space for the solver to use. So here's some more examples. This would be only 1 and 3 are available. So we have the 1-bit and the 3-bit set. Now here, I've put up 2 cells. We're still talking about this cell, but this is another cell in the row. So you'll notice that only 1 is possible in this cell. There's no other possibility. So that's why I wrote it as a big one. But this other cell in the row still thinks one is possible, which means we haven't propagated the constraints. We haven't applied that one and done its eliminations yet. And that's what this zero means. This zero means, hey, it's a single, but we haven't done anything about it yet. So we apply it, we eliminate the one from this other cell in the row, and then we set this to one saying, we're done with that cell. It's been propagated. We don't have to propagate it again. And then the puzzle is done when all of the cells have been propagated, or a single value that's propagated. You can only propagate it if there's only one value left. So as we're solving, we never add possibilities, we only remove possibilities. And so we remove possibilities until there's only one left in the cell, and then we propagate it. I feel like there's probably questions at this point about that. If not, I can continue. But
I am not seeing any, but please continue.
did that make sense to you at least?
Yeah, I think so.
Okay.
In my limited technical knowledge.
Yeah. So this is kind of about as technical as it gets, but I kind of wanted to talk about this as kind of how do we actually represent things?
Yeah,
All
no,
right.
yeah, I
So
get it.
now the entire grid is, say, 81 cells, like it's a 9 by 9 grid. It is very tempting to represent that as like 9 rows, right? Make it actually 9 by 9, like a two-dimensional array. I would recommend not doing that. I would stick with a one-dimensional array and just have 81 cells, right? It's just where, however big it is, n times n cells. And so on the very left, the very first element of your array is going to be row one, column one, then row one, column two, etc., until the very last entry in your array is row nine, column nine. Um, okay, it looks like we do have some questions in chat if you want.
Yeah, whereas Malrog was a bit slow with typing. He said, asked, why did you choose the most significant bit for the propagation flag instead of the least significant?
So the advantage of this is the kind of low level instructions that I can do to set and unset bits um, makes it very convenient to have the zeroth bit be the first digit. Um, and so that it gets a little bit technical, but this decision was on purpose. And actually, I used the very most significant bit for this. I used bit number 31 for value propagated, and then all the other ones are that, because then we can, it is technically like it wouldn't be too bad to have the least significant bit be whether it's propagated, but I think it's going to make some of the shifts and masking a little bit more difficult to handle. But I mean, it would work. It's a bit of an arbitrary decision on my part that made a lot sense to me.
And then Palfy asked, if there's a variant in it, is it not propagated until that constraint is fulfilled, or is the propagation for classic only?
Propagation is for all constraints. So if you're doing a variant, it's also going to propagate the variant constraints. Um, and I'm going to talk about how the variant constraints do that a little bit later. So I'm not going to get too far into that right now. So look
Mhm.
forward to that as part of the answer.
Okay, cool.
All right. So we're representing the grid as an array of cells, and that makes there's some very straightforward math that you just have to implement once as helper functions. But the math is okay. If I want row n, column m, then this is the equation to find where in the array that is. And if I have an entry in the array and I want to know what n and m are, then this is the equation for that. And it involves division with floor and remainder after division. And if you're at all familiar with how to flatten a 2D array, this is just all that is. And then these plus ones are because um, we don't use row zero, column zero as the first cell. We use row one, column one as the first cell. So that's what that plus one is doing, and that's what these minus ones are doing. So this is mostly for display purposes, and also for constraints like anti-night, where it's like, hey, I need to go two up and one across. We need to know what that means in terms of where in the array that is. All right. So this is for the people actually trying to implement it. Feel free to ignore the next 30 seconds if if you don't care about programming. This is the one little bit that I was talking about at the beginning where we're going to get a little technical. But it's important. It's extremely important that your grid representation is compact so that it fits in the cache easily. And hopefully, many of them fit in the cache and is one block of memory, and that you can copy it as quickly as possible. You do not want indirection in there. You don't want extra allocations for each one. You want one single allocation that is extremely fast to copy with no logic to copy it, just allowing it to split. And so in C sharp, I use a uint array. In Rust, I use a vector of U32s. And in JavaScript, I use a uint 16 array or uint 32 array, depending on whether it's bigger or smaller than 15 by 15 grid. And I pool them because what you'll find in JavaScript is that creating a uint 16 array or uint 32 array is very slow. But once you have one, copying it is extremely fast. And so by pooling it, instead of deallocating them, you pool them. You only have to create a few of them. And then during your backtrack solve, you're going to be able to reuse those and clear them out and copy them as you need to. Oftentimes, you don't even need to clear them because you're going to be copying over into it anyway. All right. So that's the technical part over. I'm happy to answer questions about that technical part if anyone has them, but I'm not expecting the audience to be asking that right now. But should I continue or?
Actually, so frequent. There's a chatter frequently confused had a question. I'll read it. I have no idea what it means. It says, "Why not Prolog?" Question mark.
These are the three languages I've used. I haven't really used Prolog, but you could write a Sudoku. So I did say I was going to be language agnostic here. These are the three languages I've used and profiled and experimented with. So I know that these are going to be the ones you want in these languages. I don't know what you want in Prolog. I don't know what you want in Python. If you're going to be using an interpreted language, it's going to be slow no matter what. But you could still do certain things to make it faster. If you want a fast solver, I highly recommend at least one that is just in time compiled, like C# or JavaScript.
Mm-hmm. Okay.
And in JavaScript, you need to be very careful because some things are just slow for no reason, and some things are slow in one browser and fast in another browser. But so JavaScript's its own animal. But the advantage of writing it in JavaScript is that it can now just run in browser on anyone's browser, on the phone,
Mm-hmm.
whatever.
And Kodud says, "What's your favorite programming language?"
I really like Rust. It's not my most used language, but I really, really like the language ever since I learned it. I think it's a very good language. The language I use the most these days is C sharp, though.
Mm.
And I think it's a very C sharp is also a very nice language, but I like Rust better.
And I think now people are just asking questions because I'm like sitting here having no idea what they're meaning. Sven says, "Have you compared bun.js to node.js for performance?" I guess.
No, I haven't.
No. I swear they're now just trolling me in the chat, so I would say let's just carry on.
Malrog's a C++ dev. Yeah, so I used C++ for probably 20 years, and then I discovered Rust, and I never want to write C++ again. So anyway, so here's just a little tip. We want to copy as little as possible. I kind of touched on this. So you only copy. So copying the grid is an operation that's going to happen a lot because we have that backtracking solver. So we need to build up a stack of grids, and we're constantly backing them up in order to be able to backtrack to it. And so first of all, when you copy the grid, you don't need to copy all the constraints that go along with it and all the metadata that goes along with it. That can be shared among all the grids as long as you ensure that you never write any code that changes those things during a solve operation. So you only need to copy the grid representation itself, and you shouldn't have to copy anything else, with a little asterisk that sometimes you need to copy other things. But I would do so in a lazy manner, if that means anything to you. So we're copying only what's needed and we're sharing what doesn't change. And then we're making sure we don't change it during a solve. All right. So let's talk about classic Sudoku and constraints. So what is a constraint? It's just a rule the grid must follow. If we didn't have any rules, there'd be no way to solve it. even classic Sudoku has rules. It has 3 rules. It says digits can't repeat in a row, digits can't repeat in a column, and digits can't repeat in a box. So with those rules but then there's other rules that you might not consider a rule, which is there's a given 1 in row 1, column 1. So row 1, column 1 must be 1 is a rule. Row 3, column 3 must be a 5 is a rule. And so the set of basic Sudoku rules plus the givens are the total number of constraints in a classic Sudoku. And those constraints are what make the puzzle unique and what give it logic. So with classic Sudoku, we only need one kind of constraint, which is candidate level enforcement, what I call weak links. I did not invent that term. You might also call it a binary implication, if you'd like to call it that. But the basic concept is something you learn in Logic 101. If you've ever taken a math course that involves logic, A implies not B, and B implies not A. So this is what's called a weak link. And what is A and B? Well, it's the individual candidate 1 in this cell and the individual candidate 1 in this other cell. So if these share a row, for example, then if this one is true, so if this cell is a 1, then this cell cannot be a 1. So this one is not true. And then we also have it on the 2s. If this cell is a 2, then this cell is not 2. And also the other way around. If this cell is a 2, then this cell is not a 2. That's a weak link. And so what we're going to do is we're going to store all of the weak links for every candidate. So there are, if I'm remembering right, 729 candidates in the grid, 9 times 9 times 9. And for each of those, there is a list of other candidates that can't be true if that one is true. And so we store this A implies not B. We store that separately from B is not implies not A. Any questions about weak links? Because we're going to be using them quite a bit. I'm hoping what I said made sense to most people.
Yep. Sorry, I was on a
Okay.
different.
I think we're good.
Yeah, I get weak links and strong links myself.
Okay. Cool. And we're storing a list per candidate. And this is list, it's shared among all copied grids, right? That it's not going to change. The weak links don't change. It's just part of the rules. So a classic 9x9 Sudoku has 14,580 weak links, just to give you some perspective there. And I am not including weak links within a cell, because technically the 1 in row 1, column 1 has a weak link to the 2 in row 1, column 1, because row 1, column 1 can't be both a 1 and a 2. My solver assumes that you only have one value per cell anyway, so I don't have to encode that as a weak link. It's a built-in rule of the solver that anything that it's solving can only have exactly one value in the solution per cell. And so with that, I only need these 14,580 weak links. There are, if you think about it, a single cell eliminates from 20 other cells. There's 8 in its row, 8 in its column, and an extra 4 in the box. And then there are 9 candidates in a cell, and there are 81 cells. If you multiply that together, you get 14,580. All right. Now let's talk about variant constraints, because that's what we're all here for, right? So by the way, this is all you need to encode classic Sudoku. And this is typically how classic Sudoku is encoded if you're using something like a SAT solver. If you're using a generic logical solver that isn't specific to Sudoku, you encode these weak links. And then you also, of course, you have to encode the givens as well. The way that I encode the givens is just by eliminating all the other digits except for the given. And that's just done during initialization. So I don't really consider that to be a separate constraint, but it's just something that's done at the start. All right. Looks like we've got about 20 minutes or so.
A little longer. I think we have you
Okay.
going about half an hour, I think. So
Okay,
no.
great. So let's talk about some variant constraints. Many of them, and some you'd expect, some you might not expect, can be encoded completely with weak links. So let's talk about that. Anything that's non-repeat, like that's just the same as Sudoku, classic Sudoku. We're just doing more of it, right? So an extra region, a sumless killer cage, which is just similar to an extra region, disjoint, diagonals like Sudoku X, anything that's non-repeat can be encoded completely with weak links. The chess constraints, anti-king, anti-knight, anti-taxicab, anything where it's like if this is a one, then this other cell that in physical relation to it can't be a one. That's a chess constraint in my mind, and those can be completely weak links. And what I just described is a weak link, so that makes sense. Anytime you have cell pairs that are restricted to some rule, you can encode that rule in weak links. So crop key, if they have to be consecutive, then if a cell is a two, then the cells next to it have everything the two eliminates everything except the one and the three. It eliminates the 2, 4, 5, 6, 7, 8, 9. So it's just a bunch of weak links from that 2 to other values of whatever is next to it. So that, the ratio constraint, 1 to 2 ratio, you just encode that in weak links. XV even, summing to 5, summing to 10. If there's a 2, then the other one has to be a 3. So the 1, 2, 4, 5, 6, 7, 8, 9 get eliminated. They have weak links with the 2. And that also includes their negative constraints. So if there is not a dot present, so it can't be consecutive, then the 2 would eliminate the 1 and the 3 next to it. So cell pairs can be done. Clones should be fairly obvious how clones work, but I'll go over it. If this is a 1, this other thing has to be a 1. So the 1 has a weak link to the 2, 3, 4, 5, 6, 7, 8, 9. It might be good to build in the concept of clones at a lower level in the solver. I have not, though. I literally implement it with these weak links. Inequalities. So fortress, thermos, less than Sudoku, greater than Sudoku, whatever it is. Any inequalities, like if there's a greater than sign and you fill in a 2, then that eliminates the 1 and the 2. And thermos are just a bunch of greater than signs next to each other. There's nothing special about a thermo there. Indexers are like the 159 constraint, which has kind of fallen out of style. So I don't even know if that's a good way to reference it. But it's like this cell tells you where the 1 is in the row or the column or whatever. And so, like, if it's a 2, then that means that the 1 has to be in the second cell. And so it eliminates the 1 from all the other. So the 1, the 2 in this cell eliminates the 1 from all the other cells except that one, and eliminates the 2 through 9 from that cell. So that's how indexers are implemented. And then these are the surprising ones. Renban can be done with weak links. Nabner, entropic, modular, and whispers lines can all be done with weak links, which I'm not going to go too far in the details, but it's fun to think about what can be done with only weak links. All right. Now, you'll notice some glaringly missing constraints from that, such as killer cages, little killer, things like that. Anything that involves a sum, you're going to want a nice generic sum utility. And here's my recommendation. You want to split cells into non-repeat groups. So you basically need to implement this as some functionality that's kind of pre-processed in some way. You don't necessarily want to do this real time unless you have to for whatever constraint it is. But you have some set of cells. You want to determine, is this one? Yeah, this one thing. You want to determine how you can best split it up so that they're in the fewest groups possible. And within those groups, digits can't repeat. So, for example, if the entire sum is contained within a single row, then you just have one group. But if it like spans diagonally across a box and and repeats are allowed in this constraint, then you would need like two groups there. And so my recommendation is to just use a greedy algorithm where you just try to find the most number of cells that can be in a non-repeat group, and then you sort of make a group out of that and then remove it from the pool and then find the biggest one next. Biggest one's next. It's not going to be perfect, but it's going to be good enough. So what do we want to be able to do? What do we want to be able to do to those groups? Well, we want to be able to figure out what is the minimum sum and what is the maximum sum. We want to be able to do that very quickly. So even if it's a little bit wrong, as long as it's wrong by being too big of a range rather than too small of a range, that's usually actually fine. But you want some granular min max for that group that can be calculated quickly. You want and that is the sum range. These are the same thing. I don't know why I put that twice. But then you also, for some things, it is helpful to be able to enumerate exactly the list of possible sums, like maybe summing to 5 isn't possible, but 4 and 6 are. This is going to be slow, much slower than this, but sometimes you want to be able to enumerate like this is what's actually possible right now, and oftentimes that's when you're using like the human like solving techniques that you might want to build off the fact that 5 isn't possible to sum to. All right. And then the other thing you want to be able to do is enforce a list of sums or a range of sums or something like that to say, hey, the list could be of size 1, like this has to sum to 5, or this can sum to 3, 4, or 5, right? And then by enforce, I mean it should be able to tell you what can be eliminated because we want to enforce that list. So if you have two cells that can, or like two cells is a pair, so we don't do that. But three cells that can sum to a maximum of say 9, then you definitely can't put sevens, eights, or nines in it, and so it should enforce that and eliminate the sevens, eights, and nines. So this is um, the sum utility. And as Juggler said, also good technique for human solvers. So while you're solving these kinds of sums, there is kind of an analog to that where you want to be able to group things together, figure out mins and maxes, figure out if certain sums are possible. Did you see anything else in chat before I continue?
No, but I had a question myself. I remember
Yeah.
the last time you mentioned about negative constraints, and I remember at SudokuCon you said that negative constraint. I remember it because you made a joke about it, which was actually very funny. You said it doesn't necessarily work great with negative constraints, so I just suggest you don't set with them. But um, but I guess do you have an understanding or of why some negative constraints it doesn't necessarily play a role?
So what I was referencing there is if you're going to use true candidates, the assumption is that anything you add to the grid will only restrict those candidates. And negative constraint violates that because if all dots are given, right,
Mm,
then what you're currently seeing with true candidates is assuming that the dot wasn't given
I
between
see.
some cells. So then when you give that dot, it's going to change what's possible throughout the
Mm,
entire puzzle.
right.
And so we break that kind of idea that as we build the puzzle, we're continuously restricting it. Whereas like adding a dot could increase the number of solutions,
Mm,
right?
I see.
And so there have been suggestions on how to kind of make it a little bit more, yeah, like a little bit easier to set a negative constraint puzzle. But like for example, having a dot you can place that says there may or may not be a dot here, so don't enforce any constraint.
Mm,
And you kind of just place them in a bunch of places where you may or may not want to put a dot. But it's still quite awkward, and
right,
I haven't
right.
implemented that.
Okay,
So
cool.
what I was talking about back here is just it's not hard to encode a negative constraint.
Mm,
Um, Not hard to encode it, but as a tool with true candidates,
yeah,
you can fall into some traps with that.
right, right. Okay,
All right,
cool.
let's move on. So with the sum utility, it makes a whole lot some constraints a whole lot easier. Killer cages, little killer, which is this whole diagonal must sum to something, and little killer is the big motivation along with arrow to group the sums because a little killer is only ever going to have at most 3 groups. But if you don't account for that, then the range of possible sums is huge and they're very slow. But once you treat it as a group, a set of up to 3 groups instead of up to 9 cells individually, it suddenly speeds up the calculations quite considerably. Um, Arrows, but only single sum arrows, not pills. Because with arrows, what we can do is we can say, well, the circle itself right now it can be a 3, 4, or 5, and then the line can be a 4 or a 6. So the answer is we put a 4 there and we use the sum of 4, right? So you can kind of do comparisons between possible sums with arrows, and other techniques like that. Region sum lines, obviously, what you can do is you can say very similarly, this part of the line has this list of sums possible. This other part of the line has this list of sums possible. Let's cross reference and enforce only the intersection of those two options. Double arrow, which is a Zeta math invention, very similar to region sum in concept, where it's, these two cells need to add to the same as this other set of cells. And so you can see how these utilities make a lot of things much easier. And actually, you can boil it down to just implementing these very generic ideas. You've got the constant sum constraint. That's going to be killer. That's going to be little killer. With a constant sum, it's like this is going to sum to 10. So you want to be able to enforce that on a set of cells that they must sum to 10. And then equal sums, where it's sum, this set of cells must have the same sum as this other set of cells. And so if you implemented that, then you can implement all of these and more using just a specialization of the constant sum constraint and the equal sum constraint. Hopefully that makes sense.
Yeah.
Can you name one that's glaringly missing from here? I mean, other than pill arrows, which I just talked about.
As a sum constraint?
A constraint that involves sums. Can you think of one that's glaringly missing?
Oh, oh man.
Maybe someone in chat can.
X sums?
That's one. Yep. Sandwich. I saw one muncher say
Sandwich?
sandwich.
Yeah.
Those are still hard. I can talk a little bit about why. So arrow
Oh,
pills.
between lines. How could I forget between lines as well? Anyway.
Yeah. Well, it didn't involve sums, so
Yeah.
that's why you didn't think of it. Same as skyscrapers. So these sum constraints are still difficult, not limited to sums. 10 lines is on my list too. Good job, Rockrat. So arrow pills, they're hard because it's not an equal sum constraint. You have to interpret the pill as a number string. So like the second one is multiplied by 10. And so that just makes it much more complicated to implement. XV I mentioned in the weak links. XV can be done via weak links. Limit. All right. Between lines is hard because you don't know which end is the smaller end. So you can't encode the weak links for it. You have to just do specialized logic that accounts for both and like unions them until it figures out which end is the bigger end. And then it can be encoded with weak links because then it's just a bunch of like less than constraints. Sandwich is hard because even though it's an enforced specific sum, you don't know which cells are involved in the sum until you find where the 1,9 go. So notice a lot of these have involved conditionals. This one's just hard. I just wanted to call this one out. Just don't use arrow pills, and then I don't have to code them anymore. That would be nice. What's frustrating about arrow pills, if I want to rant a bit more, is they take the longest and most complex code to implement, and then no one ever uses them anyway. So
Well, I will say, I don't know if you watched earlier, and everyone was demanding that I put like a lemon in the grid, and I tried, and someone was like, I don't think Rangsk solver is going to like this. So I said, you know what? I'm going to take it out, and I will put one in, but I want to make sure we have like, I don't know, 10 other digits in the grid, so it doesn't
yeah.
me.
Yeah, it's complicated. It's slow.
Yeah.
And I never want to touch that code again, so I'm not going to improve it.
Yeah.
All right. Skyscraper, obviously, it's just very specialized, right? Skyscraper is just like a super specialized constraint that doesn't have an analog to weak links or sums or anything like that. It's just you got to code it. You just got to be very specific. 10 lines are hard because you don't know where the segments are. So it's not just figuring out how to add to 10, it's figuring out how you're segmenting this 10 line to make it add to 10. So you notice that's a similar issue to say it's a sandwich. And then X sums, that first digit tells you how many cells to use. So until you know that first digit, you don't know how many cells are involved in the sum. So it takes some specialized knowledge to implement that. And so how do you make that fast is often the question, right?
Yeah, yeah.
And you have to do it in a specialized way.
I was going to say something you mentioned then about the 10 lines and the segments. I recall, I don't know if I recall hearing you have a conversation with someone about this, but with region sum lines in your solver, how it was tricky to have a region sum line that spanned multiple boxes and getting the solver to know that like the bit in box 1 was the same as box 2 is the same as box 3.
So that kind of would get into this if you're using generic ideas like equal sums,
Mm,
you might just implement it as this group has the same sum as this group.
mm,
But with region sum, you could span, say, 4 boxes.
yeah,
And
yeah,
so with the way you would encode that is group 1 is the same sum as group 2 is the same sum as group 3, and group 3 is the same sum as group 4. But it would actually be better to encode all of those relationships, like 1 and 3 and 1 and 4 as well,
yeah, yeah,
2 and 3, 2 and 4. But still, then it's going to have to propagate the deductions. So it would be better to have an equal sum that says any number of groups can be specified that are all equal, and then it's smart about how it handles that.
yeah.
But I think maybe the discussion you might be thinking about, and I'm trying to read your mind here, and sorry if I'm wrong, but the other discussion that often happens with region sum lines is what do you do when you re-enter a box? Because when I
Yeah.
initially implemented it, I implemented it as all of the cells in the same box are treated as a single sum.
Right,
But
right.
then a lot of people were building puzzles where re-entering a box started a new sum. And so you could have the line go, out of the box and then back into it, and those within that box have the same sum as each other.
Yeah.
And that ended up being kind of the standard. And so
Mm.
now the rule is kind of when you cross a box border, um, it starts a new sum. And so I actually changed my solver to implement it that way instead of the other way
Yeah, actually, yeah, I
recently.
might have been thinking of that one, but yeah, you're right.
Yeah.
It was the two different flavors, I guess, of Region Sam, and there's a discussion about which is better or not. So, um, Malrog was saying he found it strange to see X sums on the list because it intuitively felt more constrained, but Juggler was saying that you just still need to write the custom code for it, I guess, rather than it's
Yeah, exactly. So what I'm talking about is you're asking for this to be implemented in the solver. If it's one of these, and I can do it with weak links, I can get that to you in an hour, right? It's very, very quick to implement, and the solver is already going to have a bunch of mechanisms within it to handle and optimize weak links. If what you're asking for is something like a weird skyscraper variant, I'm probably just going to say no, find someone else to implement it because I don't have time because that's going to take me days and a lot of testing, right? That's what I mean by difficult. And some of them are also more difficult for the solver because custom code doesn't benefit from external optimization. This is the final thing. These are the most trivial. Just in initialize. Um, sorry, we're going over the methods now, but um, sorry, what I just said is wrong. What we're going to talk about now is how are the constraints actually implemented, and it sounds like I have maybe 10 minutes left. Is that right?
15, 10, 15, yep.
Okay, great. Um, there's three things that a constraint implementation can implement. They, um, they don't have to, but if you don't implement any of them, then you don't get anything. Um, and I will say, outside of this, a constraint can also just add weak links to the list of weak links. And if it can be completely implemented that way, you don't have to implement any of these because you can just add those weak links. So if you have something a little bit more complex than that, these are the three things that it does. First, it has an initialization that just happens once when the constraint is added to the grid. And that's just going to seed the grid with what I call trivial eliminations. What do I mean by that? Well, if you've got an even or odd constraint, in initialize, the even will eliminate all the odds, and the odds will eliminate all the evens. There's no actual logic to even or odd. It's just kind of like a weak given, if you think about it that way. A given would be in this list as well. Um, thermos. Thermos can't be completely implemented with initialize, but there are certain things people expect, which is like, if I have a thermo, you're not going to say from the start that 9 is possible in the bulb. I would like to, as soon as I start, for those candidates in the thermo to already be at least the trivial idea. Same with killer cages. If I have a 3-cell cage that sums to 9, I don't expect 7, 8, and 9 to be in that cage right at the start. I expect those to already be eliminated. German whispers, like in a 9 by 9 German whisper, everyone knows you can't put a 5 on the whisper. So let's just eliminate 5 from the whole line right from the start. That kind of thing. So it's up to the implementer of initialize to determine what is a trivial elimination. But it's just kind of the thing of would they want to see that as a step? Like, oh, the even constraint as a step that eliminates all the odds from the cell, or does the even constraint just start out already with that eliminated? All right, the next thing is enforce. The job of enforce is to determine if the constraint has been violated. Have we broken the puzzle? So, for example, if 1, 2, and 3 are in a 3-cell killer cage that's supposed to add to 9, well, that adds to 6. So the enforce step will say, "Hey, something's wrong here," and that informs the solver that this grid is now invalid and cannot be continued. Avoid, this is just a tip, avoid double enforcement of weak links. If you've already registered a weak link, you will never encounter a situation where that weak link is violated. So there is no reason to double enforce that. So if you have a pure weak link constraint, you do not need to implement enforce. And I will say that fast early detection is important. Um, if you can think of a way to do it quickly, it is good to put it in enforce. So, for example, you may be able to determine a little bit earlier that the sum can't be reached, for example. So a 3-cell 7 cage, and you've now put a 3 in there. You might want to detect right away that, oop, this is a broken puzzle before you fill in the other 2 cells and then say, hey, the sum isn't 7. Little things like that. That's just a weird example, but it's an example to show what I mean by that. All right, here's some more examples, which I forgot I put on the slide. Yeah, minimum sum is too high, or the maximum sum is too low. So we just literally sum up the 3 smallest values that are available in these 3 cells, and that's higher than the sum already. Well, we're broken, for example. Or, we know that a Renban can be implemented with only weak links, but it's still good to add an enforce, because Renban implies, like, a 5-cell Renban must have these digits on it. And so if now we cannot place that digit anywhere on the red band, we're broken. We should detect that early. Otherwise, the solver is going to have to fill out the whole red band and discover that it's not possible. And it's going to do that over and over and over again. So this is like tree trimming. This is saying, hey, we've detected we're invalid. Let's not continue. All right. And then the final thing it implements is the logical step. We perform logical eliminations. So there's kind of a choice you make here, and you may even do different logic in 2 situations. The choice is this happening during the fast solver where we just need to know, yeah, we're going to be doing a lot of guess and check anyway? Or is this happening in the human solver where a human is expecting us to report certain pieces of logic about this constraint? And so you want to determine whether something appears fast enough and valuable enough to work in the backtracking. And honestly, a lot of that just is trial and error. Like, let's try including that and then testing a bunch of puzzles and seeing if they get faster or slower. And so, yeah, some human logic's expensive, but worthwhile when logical solving. And the basic concept is it can change the grid. It can perform eliminations, and it returns whether it made eliminations. And it can also determine if the grid is broken in a more complex way. All right. Any questions about how a constraint is implemented? Because that's it. Those are the 3 things.
So is it Olamad was asking how difficult would it be to make a constraint only for a defined group of cells, for example, like anti-night in this column, and also ambiguity clues.
I'm actually hopefully have time to cover ambiguity. It's the end of this talk, so wait for that. It is not hard to implement a constraint that is confined to certain cells. It just has to get implemented, right? So honestly, like, one thing that I've been considering is just adding something to the fpuzzles format that's sent over to the solver. That's just, here's a list of weak links, and so then the client can implement, hey, they want some complex relationship that can be implemented via only weak links, like anti-night, but only for half the grid. Um, and that can then just be, on the client side, turned into a list of weak links and then just passed along with the puzzle. And then there could also be like other things like these generic sums, like, hey, we want these particular weird set of cells to sum to 10, or these set of cells sum to the same as these set of cells. If that's just directly encodable as a constraint, rather than having to go through something specific like killer, then that allows the client, like the fpuzzle side or whatever else integrates it, to specify those things without my solver knowing the context. But that is not a feature of the solver at the moment. But there's a lot of different directions we can go to make improvements on that area. All right.
Yep,
Any other questions?
that was it.
All right. And just a little tip. Constraints should not store grid specific state. What I mean by that is like it may be tempting to update some internal state of the constraint itself when we encounter a grid that has been, has had some more additional like eliminations that have happened. But these constraints are shared among all the grid clones as we backtrack solve. And so that means the constraint needs to be agnostic to the current grid state, and that grid state is passed into these various methods. So the internal state can cache global things that are always true about the constraint, but it shouldn't cache anything that's based on what the grid looked like at any point in time. All right, now I'm going to finish this talk with an interesting idea. This is actually Grace Fu's idea, which I really like. Um, and it is called the OR constraint. And so this is going to address ambiguity and a few other things. An OR constraint is a parent constraint that contains two or more children constraints. So you think about a constraint that then references some other constraints within it as a child. Like um, now, because it's an OR constraint, only one of the child constraints must be satisfied. Now, more than one could be satisfied, of course, but we only have to satisfy one of them in order for the grid to not be broken. Here's some examples of where this would be useful. Notice these are the hard ones. That's on purpose. Xsum. So with an OR constraint, we wouldn't actually have to implement anything special for Xsum. All we would have to do is build an OR constraint that says this first cell is a 1 and the sum of one cell is that, or this first cell is a 2 and the sum of these two cells is that, or this first cell is a 3 and the first three cells, etc. And of course, you can be smart about which ones you make that are actually possible. But with that, then only one of those needs to be satisfied, and Xsum is implemented without any special case logic. It's just already components that already exist. Sandwich, you just need to make an OR constraint that says, hey, either 1,9 is here and the inside sums to that, or 1,9 is here and the inside sum to that. You find all the possible places that it's reasonable for 1,9 to be to sum to that, and you create all of those as children of an OR constraint. Between line could be just use this set of weak links if this end of the between line is less than this other one, or use this other set of weak links if the opposite's true. 10 lines, you just find all the reasonable ways that the line could be partitioned, and you make an OR within the OR constraint. You just enforce those sums for how those are individually partitioned. And then finally, user-defined ambiguity. So if you want to implement something that's like this line's a Renban or a German whisper, that could be under the OR constraint. And I think I'm running out of time, so we'll just speed through the rest of this. So it requires the simultaneous solving of subproblems. So each of those subproblems are individually tested within the whole all simultaneously. And then you collapse deductions upward, where if every single one of these children agree about elimination, then that elimination can happen to the parent. And then you can optimize by ignoring subproblems that have become invalid. So once a subproblem says, hey, I'm an invalid grid, then you can just eliminate that subproblem because that's never going to be true, and just worry about the subproblems that can still be true. And there is a prototype of this in the JavaScript or TypeScript version of the solver, and it was implemented by Grace Fu. All right, and that is it. There's still time for questions until I'm kicked out. So if there are any last second ones.
Yeah, if there are any questions in the chat for Ranks, please type them in quickly. That was it didn't go as technical as I thought it was going to. It was very interesting hearing behind the scenes and such. And on behalf of setters everywhere, as somebody who does use your solver, I would like to thank you in particular. Um, Sven is saying, I guess the OR could also be used for constraints which may be true or false determined by the solver. I guess so, like a two truths and one lie puzzle.
Yeah, I'd have to think about. I think it would be specific to how the rules say that, but I do think the OR constraint opens up a lot of interesting opportunities where we no longer have to handcraft really specific stuff,
Mm,
and so
mm,
a lot of ambiguity stuff is opened up. Um, I will say the OR constraint comes with a good amount of overhead to it and complexity to the solve. So I wouldn't expect the solver to be quite as snappy when you use constraints that involve OR, but um,
mm.
certainly useful.
And then Paulfly just is wondering what the best way to implement. Of course, Paulfly is talking about remote sums. Would there be a way to implement remote sums?
Remind me the specifics of remote sums.
So remote sums, you have a cage and a grid, usually in a single cell with a sum in, and I guess it. So if you had, say, row one,
Oh,
column
and
one,
it indexes, right?
and it's kind of a number of steps away. So it would be like, say, a three. If it were a cage that had a four in,
Mhm.
and the cage had a. Sorry, let me back up. If the cage summed to four and it had a three in, then it means that three steps away in some direction, there has to be a one that it sums to.
I think that can be implemented with weak links
Mm,
because the two would have a weak link to that second cell to say that that second cell must be um, say another two if the sum was
yeah.
four. Um, and so that means you can do that with weak links by eliminating everything but four.
Okay.
So the two would have a weak link to everything but four in the second cell. The three would have a weak link to everything but one in the third cell.
Hmm. Okay. Cool. Okay. Yeah. It looks like we're about hitting the time though. So again, thank you, Ranks. That was a really cool talk
Yeah.
and done in relatively short order because I know we you volunteered for this segment relative a couple of weeks ago. So thanks again.
Yeah. I put this talk together very recently, so I'm glad it went smoothly. I hope it
Yeah.
was interesting for everybody.
That was great. And yeah, is there anything you want to plug again before we go to break?
Yeah, if I just go back to the start, I'm sure there's an easier way to do that. You can find me on YouTube. I'm Rangsk on YouTube, TikTok, Rangsk_YT, Facebook and Instagram. I'm Rangsk Puzzles. You might enjoy my content, Sudoku and otherwise. So yeah,
Okay,
check me out.
cool.